In this video, we're going to look at gas pressures. And essentially, a gas pressure is the force exerted on a given area. And we can show that using the formula here, the pressure being the force divided by the area. And there are ways in which we can calculate this, and you can see that based on these types of calculations, you can show that certain items have more force per area even though that particular item happens to be larger than something else. And this is shown really well by calculating the pressure per the elephant foot versus the pressure of the skate blade. And so if we had a 14,000 pound elephant, and it turns out we could do some dimensional analysis here where we say we have one element has 4 feet, and then for every 1 foot, that has an area of 250 square inches. If we do our math, our calculations here, it ends up that we have a pressure of 14 pounds per square inch. And then if you calculate that for the skate blade, say you have a 120-pound skater, for every 1 skater you have 2 blades, and for every 1 blade you have 2 square inches. And if you do this calculation, you end up with 30 pounds per square inch. So even though you have a small skater and a small blade, the amount of force per area is much, much greater. In fact, it's more than twice as great as the force being projected by the foot of an elephant. And we have several ways in which we can show the measurement of pressure. We have the SI unit called the Pascal. And the Pascal is actually a unit that has many iterations of how we can show that mathematically with units. It turns out 1 Pascal is the same as 1 Newton per meter squared. And just in case you're unfamiliar with what a Newton looks like, this is a kilogram meters per second squared. We also use the bar sometimes in meteorology, and that's equal to 100,000 pascals. In the United States and a few other countries throughout the world, we still use a type of pressure called pounds per square inch, or PSI. And a PSI is equal to another type of unit where you have 14.7 PSI is equal to 1 atmosphere. Well, what's an atmosphere? An atmosphere, using the abbreviation ATM, is actually the value we give of 101,325 pascals, which 1 atmosphere is what you would be at sea level. If you were on our planet at sea level, we call that a single atmosphere. There are a few other units that are highly used, especially in chemistry. One is called torr, and torr is a value of 760 torr is equal to 1 atm. And they're also equivalent. 1 torr is equal to 1 millimeter of mercury. And so what is a millimeter of mercury? So where that was first found was when we were trying to figure out a way to measure what we call in meteorology the barometric pressure. Well, the barometric pressure is the pressure that you're feeling at the time of wherever place you're located on a planet. And so if you happen to be at sea level, that barometric pressure would be one value. And then if you're on top of Pikes Peak, that pressure would be a different value. Well, one of the ways that scientists started to try to figure that value out was by using substances in a hollow tube that was closed on one end, and they would fill that tube with that substance and then turn it upside down and put it into an open container of that same substance. And it turns out that the substance would come out and you would have a particular level or value or distance rather of how much that substance would stay in that tube, and that value could change based on the pressure that the atmosphere was pushing down on the top of that substance in the open container. And it turns out if you do this at sea level with mercury, Hg is the symbol for mercury, then the the distance that it stays in the tube above the level of the mercury in the open container is about 2.5 feet, or we actually really call that 760 millimeters. This is where we get the term 760 millimeters of mercury. And so we use that as a barometric value. Now, you could do this with other substances. However, how we calculate that height is based on this equation over here that's called the hydrostatic pressure equation. And how you calculate that hydrostatic pressure is a product of the height times the density of that substance that's in that tube times the acceleration due to gravity, which is a constant of 9.81 meters per second squared. And so if you look at the density of mercury, which is about 13.6 grams per milliliter, then the particular height you would get at 1 atmosphere would be the 760 millimeters, or 2.5 feet. So you'd really only have to have a barometer that has a tube long about 3 feet long, so that you would have enough space for that mercury to move up and down as the barometric pressure changes. But if you were to do this with water, the density of water is 1 times the acceleration of gravity plus the putting in of the atmospheric pressure. The height you would calculate, guys, would be up to 33.9 feet. Well, obviously that's we can't do that. We can't have a barometer that's the height of a 3-story building. So we don't use water as a substance to put into a barometer. We have to use something that has a much greater density. And so this is why mercury was very, very prevalent into a lot of our barometers starting out. We also have another method of measuring pressure, but this method is to measure pressure of a substance inside a container, like a gas inside of a container. And since we will use manometers, is what they're called, to measure the pressure of gases inside a container, especially if you're working with substances that are gases. There are 2 kinds of manometers. There's one that's called a closed-end manometer, and there's one that's called an open-end manometer. And the equation that you would use to calculate the pressure of that gas is the same as the hydrostatic pressure. So you'll use the product of the height times the density times the acceleration due to gravity. And the height that you would use is the height of the difference on the left-hand side of a liquid substance to the height of the liquid on the right-hand side of the tube. And so that difference in height here is what you use in H in that equation, along with the density of the liquid and your constant of acceleration due to gravity. And that's how you would calculate that gas's pressure. Now, in an open-ended manometer, there's a little bit of a slightly different thing you have to do. You'll take the atmospheric pressure of that day, because the atmospheric pressure actually pushes down on the substance as well. And what you'll do is, if the level of the liquid in the manometer is below the level on the left-hand side, then you would subtract that product of the hydrostatic pressure. But if it's higher than on the left-hand side, you would add the hydrostatic pressure value to the atmospheric pressure. So you just have to pay attention to how that manometer reads as to which equation you would use. So let's take a look at a couple of example problems and see if we can do some calculations using that hydrostatic pressure equation and our types of pressure measurements or units, and so that we can learn how to convert from one unit to the next. So in this first example problem, it says, does the hydrostatic pressure of mercury at sea level equal the atmospheric pressure at sea level? And so the atmospheric pressure at sea level in pascals is a value that has been experimentally calculated to be 101,325 pascals. So what we're going to try to do is use the equation, the hydrostatic pressure equation, to see if we can calculate that 101,325 pascals. And so we're going to use the height of mercury as 760 millimeters, density 13.6 grams per milliliter, or centimeters cubed is the same as milliliters, and the acceleration due to gravity. And so let's do this. So in order to plug all of these values in, we do have to make sure that the units are the same across the board. And if you'll notice that we have the units of distance here, millimeters, the distance here, centimeters cubed, which is technically a volume, the distance here, meters. Well, we've got to make all of those end up being the same. And since the acceleration due to gravity is pretty uniform, let's keep that meters, and let's change everything else to meters, and then we'll plug those in. So first we're going to change the 760 millimeters into meters. And using dimensional analysis, we know for every 1,000 millimeters, that's equivalent to 1 meter. And so the millimeters will cancel, this gives us meters, and the units for the value for this will be 0.760 meters, still maintaining 2 sig figs. So let's keep that in mind. If we're going to maintain 2 sig figs that was in this number, then we should do that in this number. And for us to do that, we would really need to just get rid of that 0. Okay, so we've done this one right here. Let's do the next conversion of 13.6 grams per centimeter cubed. And we'll do 1 unit at a time. So let's do the numerator value, where we want to make sure that this ends up being a unit that is something that is associated with pascals. And if you go back to our kind of diagram here of different types of units for measurement of pressure, pascals doesn't have grams in it anywhere, but it does have kilograms. So let's go ahead and move that value to kilograms. And so for every 1,000 grams, that's equivalent to 1 kilogram. And then for every 100 centimeters, that's equal to 1 meter. So we've gone through and changed grams to kilograms. Now we need to change centimeters to meters. But you notice how this says centimeters cubed and this doesn't. Well, we've got to fix that. So what we're going to essentially do is cube the entire conversion factor. Now when you do that, you distribute that cubing to every number and unit within that conversion factor. So that means that when you do that, you'll distribute that all the way through. Okay, and so I typically don't write my conversion factor in this method. I will do it this way. I will write my conversion factor original, and then I'll go through and I'll cube everything within that conversion factor. And now centimeters cubed cancels, and that leaves you with meters or meters cubed. And the value for this ends up being in 3 significant figures, because these numbers all here are considered exact numbers, so only this is counted for sig figs, is 13,600 kilograms per meters cubed. Okay. So now we have everything in the proper unit. How about we plug everything in? So remember, it's pressure equals height times density times acceleration to gravity. The height that will be 0.76 meters. The density is 13,600 kilograms per meters cubed. And then the acceleration of gravity is 9.81 meters per second squared. And so when you do this, the value you end up getting, and we're going to round this to 2 sig figs essentially, is, and on my calculator I get something around 101,000 and some change. But note that I need to round that to two significant digits. And so that would be pretty difficult for me to take in this 1 and round this up or down. It's going to stay down, which means it ends up being about 100,000. Well, if you write this value, that's only 1 sig fig. So the only way to really write this number in two significant digits is to put this in scientific notation. So I'll just move this decimal over 5 times to the left. I'll put a decimal here, and then I'll write this as 1.0 times 10 to the 5th. And that will be kilograms per meters second squared. And what you'll notice is this is not written in a unit that makes it where we can compare to this value. Is that value the same value? Well, it turns out if you do some working through a Pascal that is equal to a Newton per meter squared, and what a Newton is a kilogram, meters per second squared, this actually ends up being the same as a Pascal. So in reality, this is 1.0 times 10 to the 5th pascals. And so let's compare that number to the original number, 101,325. That's pretty close. That's pretty close to the same value. So I say that yes, the hydrostatic pressure of mercury at sea level is the same as the atmospheric pressure at sea level. All right, let's go to the next problem. This is an example problem where we're using a manometer. So it says the pressure of a sample of gas is measured with a closed-end manometer. So that means the equation we're going to use is this. And the liquid in the manometer is mercury. Okay, great. So that means we know what our density is, which is awesome. Determine the pressure of the gas in pascals, torrs, and the bar. So this is going to be kind of we're using the same equation as previous, but we're going to try to solve for this in 3 different units. So let's do the first one, A, the Pascal. And so the pressure is going to be the height. So the height we're going to use actually is the height here. So we're trying to find the pressure of this gas. And remember, we're using the height that's the difference between the left and the right tube on the manometer, which is 6.0 inches. Well, to be able to plug into this equation, we're going to have to figure this out in meters, because remember, our gravity value is in meters as well. And so we'll do that really quick over to the side. 6.0 inches. We're going to convert that. I'm going to go through, I think, centimeters. So for every 1 inch, that's equal to 2.54 centimeters. And then we'll convert centimeters to meters. For every 100 centimeters, that's equal to 1 meter. And then it ends up being a value of 0.15 meters. So that's the value we're going to use. So we can start plugging things in here. So we're going to 0.15 meters. We do have to change our unit of centimeters cube into meters cube for our density, but see, we did that in a previous problem. So we're still going to just use this value of 13,600 kilograms per meters cubed. And we also have the kilograms changed from grams. And then the gravity, 9.81 meters per second squared. And when we do this math, we end up getting a value of 20,012.4 pascals on the calculator, and we have to make that a 2 sig fig value. So we're going to have to put that in scientific notation of 2.0 times 10 to the 4th pascals. And I'm just kind of, we got the same kind of type of unit of kilograms per meter squared as previous, and just note that that is the same as a pascal. That's why I wrote that as pascal. Okay, so we've got part A. What about part B? My suggestion here is just let's take our pascal value we just calculated and just convert it to a torr. So if we start with 2.0 times 10 to the 4th pascals, let's convert that to torr. So you might need to go back and look at your units of pressure in order to do this. And there's a couple of things these might get to a point where you memorize these and whatnot. But I know that I'm going for this particular unit here, and I've got to figure out some way that this stuff is equal to a Pascal. Well, I know 1 ATM is equal to this amount of Pascal. So if this is equal to 760 torr, that means 760 torr is equal to that. So I know my conversion factor here will be 760 torr is equal to 101,325. Okay, so 101,325 pascals is equal to 760 torr. And I think we were, sorry, moving off just a little bit. That equals 150 torr. And so we've now calculated that value. All right. And let's do our third one, our third unit, and that's the bar. And it turns out that I'm just going to go ahead and use my original Pascal value, 2.0 times 10 to the fourth pascals. We can go back to our chart again, and it turns out that there's a really clear unit to use for conversion of bar. It's 100,000 pascals, so is equal to a bar, so that'll be pretty easy. So we'll go 100,000 pascals is equal to 1 bar. And that ends up giving us a value of 0.20 bars. And so that's that unit. In this last example, we're going to look at an open-ended manometer. So the pressure of a sample of gas is measured at sea level with an open-ended mercury manometer. Determine the pressure of the gas in kilopascals, ATMs, and millimeters of mercury. So before we get started, let's look at what kind of equation we're going to use to measure in this open-ended manometer. Remember, when you do a measurement or a calculation, the pressure of your gas is equal to the pressure of the atmosphere, either plus or minus the height times the density times the gravity. And so you have to decide which one these end up being. If the two tubes, if the height on the left is lower than the height on the right, so the pressure on the open-ended part of the tube is higher, then you're going to use the plus sign. If it were lower, you'd use the minus sign. So we're going to rewrite this equation to look like this. Plus height, density, gravity. Okay, so how do we know what this value is? Well, it says sea level, so that means the pressure, just to begin with for our first unit, is 1 ATM, or if you will, 101,325 pascals. This will probably be the most useful one since kilopascals is our first calculation that we're looking at. So we'll start with A. A couple of things that we need to do is let's calculate this section first, the height times density times gravity. And for us to do that, the height that they're talking about is this value. So we need to take our 13.7 centimeters and convert that to meters. And we can use dimensional analysis to do that. For every 100 centimeters, that's equal to 1 meter, which gives us 0.137 meters. Now what we're going to do is plug that into our equation, and we'll add that to our pressure of atmosphere at that atmosphere. So H density times gravity, this value equals the height 0.137 meters. And again, previously we've already converted the density of mercury before, so we're going to use that value of 13,600 kilograms per meters cubed, and then times our constant of acceleration due to gravity of 9.81 meters per second squared. And this gives us a value of close to approximately, in 3 sig figs, 18,300 pascals. Well, keep in mind, this is this value. So for us to find the pressure of our gas, what we're going to do is add the pressure of the atmosphere at sea level to that value. Well, sea level is 1,001,325 pascals, and we're going to add the 18,300 pascals. And so this gives us a value of 119,625 pascals. Well, we're going to need to actually make that value into the proper sig figs. And for this, I think if we round to the hundredths place, that would give us the proper unit here. And so this would be 119,600 pascals. Okay, and so that is pascals, but the question asked us to do kilopascals. So let's do kilopascals. When we convert that to kilopascals, for every 1,000 pascals, it's equal to 1 kilopascal. Essentially, we're going to be moving the decimal over 3 times to the left, and the number of kilopascals will be 119.6 kilopascals. So that is our answer to part A. Part B, we wanted to convert to ATMs. Okay, well, let's start with our Pascal value of 119,600 pascals. We could start with kilopascals, but we'd have to just convert right back to pascals. So we're going to start with our Pascal value, and we're going to convert that to ATMs. And so we know that for every 101,325 pascals, it's equal to 1 ATM. Pretty simple conversion here. And that value ends up giving us a value of 0. Oh, I'm sorry. I think I have the wrong number. It's not 0. It is 1.18. And we're going to go 80 for sig figs, right? ATMs. And so that is our conversion vector, or our value we've converted to ATMs. Last one is going to be to millimeters of mercury. So you can start technically with the pascals you calculated in part A, or you could actually technically use the ATMs you calculated in part B. It doesn't matter, they're both equivalent. I'm just going to go ahead and start with my pascals just to cut down on decimal kind of fluctuations due to rounding. And so the least amount of rounding you have going from one conversion to the next is the best. And so we're going to go from pascals to millimeters of mercury. And it turns out we can still use the same kind of conversion of 101,325 pascals is equal to actually 760 millimeters of mercury here. And so that gives us a value somewhere near 900 millimeters of mercury, but we want to make sure that we are in about 3 or 4 significant figures. Actually, it should be 4, I believe. And so this value gives you, I got 897.1 millimeters of mercury here. Okay, so that's how you use the hydrostatic pressure equation to solve for different pressures using different types of devices like barometers and manometers, and how we do a lot of conversions between one type of pressure unit to another.